This is expert TA number 9 on kinetic energy and angular momentum, problem number 9. And it says an ice skater is spinning at 6.8 revolutions per second and has a moment of inertia of 0.36 kilograms per meter squared. So part A is asking us to calculate the angular momentum in kilograms meters squared per second of an ice skater spinning at 6.8 revolutions per second. So the first thing we're going to do is turn that into radians per revolution. So we have 6.8 revolutions over 1 second. I'm going to multiply that by 2 pi radians per 1 revolution, which is going to give us 42.73 radians per revolution. And all we have to do here is 6.8 times 2 pi. And we're going to start out with our angular momentum is equal to the moment of inertia times the angular velocity, giving us that our moment of inertia is L is equal to 42.73 times 0.36, which was giving us an angular momentum of 15.38 kilogram meters per second squared. And now question B asks if he reduces his rate of rotation by extending his arms, increasing his moment of inertia. So we're increasing our I. Find the value of his moment of inertia in kilogram meters squared if his rate of rotation increases to 1.5 revolutions per second. So here we're going to start out with energy initial equals energy final. And we have moment of inertia initial times angular velocity initial equals moment of inertia final, angular velocity final. And we already solved this up here, so 15.38 is equal to moment of inertia final times our angular velocity final. And to find that, we're going to have angular velocity is equal to our new rotation is 1.5 times 2 pi. Same thing we did up here, just a little easier. Over 1 equal to 9.425 radians per revolution. So we're going to multiply this by 9.425, giving us a moment of inertia final equal to 1.632 kilograms per meters squared. So that was pretty straightforward. It's conservation of momentum and energy. And part C is saying, suppose instead he keeps his arm in and allows friction of the ice to slow him down to 3.5 revolutions per second. So we're slowing down to 3.5 revolutions per 1 second. What is the magnitude of the average torque that was exerted? So this is a torque problem in Newton per meters if this takes 14 seconds. So time also equals 14 seconds. So again, we're going to have to turn this into radians per second. So radians per revolution times 2 pi radians over 1 revolution equals, I should put seconds up there, and that is going to be equal to 21.99 radians per revolution. So now that we have that, we can have our angular momentum is equal to, again, moment of inertia times angular velocity. And we can solve this putting in our variables, 21.99, which we got from right here, times 0.36, which we got from part A in the beginning of the problem. And that gives us an angular momentum of 7.917. Now, using our equations, we also know that angular momentum is equal to torque times the change in time. And we can use this to solve for our torque. So we use our angular momentum, 7.917 is equal to torque times 14, which we got from right here. And if you do all this math, we have a torque is equal to 0.533 Newton meters. And that is problem 9. Thank you.